Hello. The first topic we have to think about when we consider the GMM estimation method is the number of moment conditions. Simply speaking, so it is related to the over-identification in the previous chapter in when we discussed the IV regression model. We considered when the over-identification happens, like simply speaking, when the number of instruments is greater than the number of endogenous variables, then you have more than enough information. Same thing happens. You have, if you want to estimate k number of parameters, you have to have at least k number of moment conditions. You may have more than that, but less than k moment conditions does not allow you to estimate all the parameters. So remember, k was the number of parameters, m was the number of moment conditions. M is from moment. So if the moment condition is fewer than the number of parameters, then the parameter is not identified. Some of the parameters or all of the parameters are not identified. So we cannot estimate. So you need to have the same or more moment conditions than the number of parameters. So when they are the same, it's simple. This is a simple case, and there must be unique solution, and nothing you need to worry about. But when you have more than k, then the parameter is over-identified, and we need to think about how to utilize all the informations and how to summarize the information. So first, let's think about the instrumental variable regression model in the simplest possible 2x3 case. There are two endogenous variables and there are three instrument variables. The moment condition can be written in this form, right? So you can find it easily. And so estimating the expectation is not a problem. You observe z and y, so you can just replace the expectation by sample average like this. So estimating these expectations is not a problem, but we have to think about the structure. So there are three equations and there are three coefficients from each equation. Then in the end, you can think about the system of linear equations like this. So a1, a2, a3, b1, b2, b3, and instead of beta 1, I use x, and instead of beta 2, I use y. So a, b, c are estimated, they are available, but x and y are unknowns. We would like to solve those linear equations for x and y based on a, b, c, 9 numbers. And as you can see, as you know, there are three equations, which is more than, we only need two equations to identify x and y. Then what happens when you have three? We will think about this simple example. So simply, suppose that you have this system of equations. System of linear equations is given by these specific numbers, and then you have to think about what is the solution. And if you do it by yourself, you can tell this easily. First, if you use 1, 1, x, y equals to 1, 1, so 1, 1 satisfies these two conditions, right? x1, y1, then these two equations are 0, but the last one is not 0. So 1, 1 means it is not 0, but minus 1. So the last equation causes a problem. And if you put 2, 0, then the first and the third one can be handled. They are 0, but the second equation is violated. So second equation becomes 2, 0, minus 3 is minus 1, not 0. And similarly, if you choose the last two equations, you get this solution, but the first equation is not satisfied. So like this, I said you need two equations, but you have three. Then in other words, you may drop one of them. Still, you can solve for x and y. The problem here is, depending on what you drop, the solution is different. If you drop say the first one or the second one or the third one, the solution changes. Then what is the solution? Then how can we choose the solution? We are going to discuss the general approach. So then maybe you can also think about this. Maybe you can take average of some kind of weighted average of these solutions. That is one possibility. Or instead of choosing two of them, so so the problem is arising from here. Just focus on the first two and then totally ignore the last one. But instead of doing that, instead of making two of them equal to 0, what I'm going to do here is, if possible, I will make all three equations as close to 0 as possible, even though they are not exactly 0. So this is our approach. We are going to make all three equations as close to 0 as possible with some certain weights. So for example, ideally, if you can make the first one equals to 0.1, 0.1, 0.1, then all the equations are reasonably satisfied with a difference of 0.1, small difference. Then that solution could be better than all of these three, any of these three solutions. So it is our approach, and that's the underlying approach beneath the GMM estimator. And then the idea is we are going to minimize the distance from the origin. So so it is exactly the idea of least squares. Least squares minimizes the residuals, which is a kind of distance from distance between the origin and the residual. So when you have scalar, the distance is defined by the absolute value. But absolute value can be also written in this form. They are mathematically the same thing. And when you have two-dimensional vector, the distance can be written in this way. Pythagoras theorem implies, so like v1 squared plus v2 squared equals to the squared of the diagonal squared. So this is the distance between a vector and origin. And even more generalization to k-dimensional case, same thing. This is the distance. Then how do we apply this? We are minimizing. We are going to minimize. So you have three things to minimize, and to minimize all the equations at the same time, we will consider three-dimensional vector. So G1, G2, G3 make a three-dimensional vector, G1, G2, G3. So if you think about the distance of this vector from the origin, then we can minimize the distance. Ideally, we hope the minimum distance equals to 0. That happens when all the equations are satisfied. But even if it is not all of them are not satisfied, still we can choose one solution using this principle. So as I said, we are going to minimize something like this. But this is not general enough. So we are going to generalize one more step. So this minimization puts the equal weight, the same weight on G1, G2, and G3. But it may be unfair if you think that the first moment contains more information than the second moment, then you have to put more weights on G1. So more weight must be put on the moment where more information is contained. right? Understand? So important moments should be taken more seriously. Therefore, like for example, you may think it this way. So 2 times g1 squared, 2 times g2 squared plus g3 squared. So g3 receives half of the weight the other two guys receive. And even more generalization is a weighting matrix. So the weight can be written in the most general form in this way. So we have squares, so you have to multiply g and g, but in between them you put a matrix. So depending on the values of the matrix W, weighting matrix, then the weights on G, G1, G2, G3 could be different depending on the weighting matrix. However, there are some restrictions. The weighting matrix must be symmetric and semi-positive definite. So because the distance must be always non-negative, it cannot be negative number, distance cannot be negative. So the matrix should be semi-positive definite, so that the distance is always positive, always non-negative. So that it becomes a distance. Okay, then in the GMM setup, you can borrow the distance, the weighting matrix, and just minimize this. So what is interesting here is I started from something equals to 0. So our motivation is to estimate the parameter based on an equation that some function equals to 0. So we are looking for the solution. So it is Z estimation principle at this point, but because of the over-identification problems, we have to choose which moment, or we have to decide how to weight those moments. So as a result, what we are doing here is we are minimizing the distance, not solving something equals to 0. We are minimizing the distance, so it becomes extremum estimator, M estimation principle in the end. So we are going to minimize moments, weighted moments. So it is a kind of a distance. And of course, choosing the weighting matrix is important. Any symmetric and strictly positive definite matrix is good, but if you choose it more carefully, then you can do better. And the simplest possible choice is the identity matrix. So put equal weights on every moment condition, then you are using identity matrix. So it is not wrong. Using the identity matrix is not wrong, but there are better ways, better metrics than the identity. So you are going to learn that later. And we will study that. And in the end, in practice, you may also choose the weighting matrix, an estimated weighting matrix. You may need to estimate the weighting matrix. Then what you need is just the estimated weighting matrix must be consistent for the metrics you want to have in the limit. Anyhow, in the end, we are going to minimize this. So from now on, we are going to discuss the consistency and the asymptotic normality, and it is a minimization problem. So the basic framework, the setup is pretty similar to the extremum estimator we discussed in chapter 3. But there is a small difference, very minor difference from the extremum estimator. So we are going to discuss that in the next lecture. My plan, so I think I can finish this chapter before the midterm exam. So my plan is your midterm exam will include up to from chapter 1 to chapter 4. If time permits, I think I'm quite slow. I'm doing slower than I expected from what I did last year. So I may need to speed up after the midterm exam, but I don't worry, it should be fine. Okay, thank you for watching. Have a nice weekend, and see you next week. Do the homework 3. And homework 2 is due this Sunday. Don't forget.